Okay, so Unit 6, we're going to start off today with, is all about heat transfer. So it's all about heat. So this is a energy unit. And today we're just going to introduce some terms and talk about how heat does transfer. So this does incorporate 3 sections of this, but they're all very much related to each other. So little definitions of some some energies. So we've already talked about light energy. We've talked a tiny bit about electrons, flowing of electrons in redox reactions, but we haven't talked about how that can be utilized for electrical energy. And then again, this unit's going to be thermal. So thermochemistry, some people call it. And heat energy is what this is going to be, what it's going to entail. And it's always going to be flowing from hot to cold. And we could talk in terms of potential energy, and we're going to have graphs in a second that are going to show this. But we could have where the potential energy of the system, whatever that system might be that we're discussing, goes from high to low. So that means it lost energy. Or we could go in the other direction, that the system starts off with a low potential energy and gains energy over a period of time. Thermodynamics, we have a definition now, heat change, and it says in chemical reactions, but we're also going to discuss physical changes too. We have actually 3 laws of thermodynamics. The only one we're going to get to in this unit is the first law. And the really important part here is energy can't be created nor destroyed. It's just going to be transferred. What is it transferred to and from? The system and the surroundings. Those are generic terms, but the system is what we're going to be interested in, and the surroundings is everything around what we're interested in. And by the way, we're going to always talk about the system by default. If energy flows into the system, energy was absorbed. And in that case, energy would be on the reactant side. If it's exothermic, flows out of the system, and energy would be on the product side. Here is some different scenarios for endothermic. So one, I think pretty obvious, but if you just heat a substance, it's going to absorb energy. But also we have phase changes. If you had a solid and it was going to become a liquid, it would have to absorb energy to do that. If you want the liquid to boil, you would have to gain, that system would have to gain energy again. And so if you put water in a pot, put it on top of your stove, turn the burner on, I think you can kind of see that that's the case. Here is something I think we'll want to go into a little more detail about. If you would take ammonium chloride, solid, and you would want to dissolve that, meaning that it's going to become aqueous. You need a bunch of things to occur. So one, I'm going to kind of go out of sequence here, but you need the ionic crystal, the Coulombic attraction between the cations and anions, to break. And when you break a bond, energy has to be absorbed. Okay? You need those cations and anions to be able to get into the water. So that means water has to break away from water. So those hydrogen bonds need to be broken, energy absorbed. And then, lastly, you need the cations to attract to water's oxygen side of the molecule. And then you need the anions to attract to the hydrogen side of water. So those are intermolecular forces that are formed, and when you form bonds, energy is released. If you add up the numeric values of those 3 things, in this particular case, the end result of those three numbers is energy absorbed. What does that mean? That means that ultimately this process is endothermic. So if you would have this going on in a beaker and you'd put your hand around the beaker, you would notice that this is getting very cold. Why is it getting cold? Energy is getting taken out of your hand. Your hand is the surroundings, and it's getting absorbed into the system. So here are the opposites, exothermic, and you can read the first two bullets here, but it's basically the exact same thing, but an opposite. But I'm going to go a little more detail with the sodium hydroxide here. So solid sodium hydroxide, if you want it to become aqueous, dissolved in water, three things have to occur, just like the last time. So in this case, the Coulombic attraction between sodium and hydroxide, that bond has to be broken. Again, anytime you break a bond, energy absorbed. The water has to break away from water. Those hydrogen bonds have to be broken, energy absorbed. And then you need the cation to attract to oxygen side of water and so forth. And that would be forming intermolecular force bonds, and energy is released. When you add up these three, not like the last example, energy is released. So energy would be over here. And so in this case, if you did this in a beaker and you had your hand around the beaker, there's energy that's coming out of this system and it's going into the surroundings. One of the surroundings is your hand. So your hand would actually get very, 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 very hot. So hot that it might burn your hand. So I just wanted to show you that when you dissolve something, it's not always going to be energy released. It's not always going to be energy absorbed. We have no numerics here. We have no numbers to be able to do this math, but in subsequent sections, we will do that. Okay, so I just wanted to show you heat transfer in case you can't visualize that. It's always hot to cold. So temperature A is more than temperature B. So the heat is going to transfer from hot to cold. That's all I wanted to show you there. And then there is relationships between temperature, kinetic energy, so forth here. If you have high temperatures, I just show that these vectors for high temperature here are kind of bigger, but they're not all exactly the same size because we talked about there's averages, but there might be some items that might be moving slower, might be moving faster. But anyhow, as something that has more kinetic energy hits something that has lower kinetic energy, it's going to transfer some of that energy. And that's all I wanted to really show with that. We've already mentioned exo and endothermic. Let's do that a little more in detail. So again, energy is released in exothermic. If we were going to quantify this, we're not quite ready to do that yet. It's going to be a negative value because you're losing that energy. Here's a couple examples. If you had a liquid that you want to freeze, energy has to be released. So if you would experience this, you could experience this with your refrigerator freezer. If you put some water in your freezer and you go to the back of your refrigerator freezer, you can feel that heat. That heat is this right here. Now, that's not the only thing that's in your refrigerator freezer, but that appliance is sucking energy out of those systems. In this case, the H2O liquid going to H2O solid, and it's transferring that to surroundings. And the surroundings, where you're going to experience that is in the back of your refrigerator freezer. There's coils back there. You may or may not be able to see them, but they allow that heat to dissipate out back there. This is, I think, an equation that you know from bio, cellular respiration, and energy is released there too. If you were going to graphically show this, and I had started to show this, for what I had done is just put 2 dots here. But you start off with high energy and you end up with low energy. How much energy did you lose? The difference between those 2 spots. Okay, and since it went down in energy, negative. We don't know what delta, well, change, delta is change. For us, H is going to be heat. Later on, we're going to experience that H has another name, but we're not quite ready to do that yet. Endothermic, exact opposites. So I used all the same things as I did before. So this would be, we could call that melting. Solid to liquid is melting. And then we wouldn't call this cellular respiration anymore. I think we'd have to call this photosynthesis. But the energy, if we were going to numerically give it a value, it would have to be a positive value because energy is absorbed. How can we show that on this graph? Potential energy starts off low and ends up high. The difference between those 2 would be our change in heat. And that's good for our introduction for thermochemistry.